The next mode of heat transfer is radiation. Radiation is the energy emitted by matter in the form of electromagnetic waves or photons as a result of the changes in the electronic configurations of the atoms or molecules. Unlike conduction and convection, the transfer of energy by radiation does not require the presence of an intervening medium. In fact, energy transfer by radiation is fastest at the speed of light and it suffers no attention in vacuum. This is how the energy of the sun reaches the earth. The heat transfer studies in fact, energy transfer by radiation is fastest. This is how the energy of the sun reaches the earth. The heat transfer studies, we are interested in thermal radiation, which is in the form of radiation emitted by bodies because of their temperature. It differs from other forms of electromagnetic radiation such as X-rays, gamma rays, microwaves, radio waves and television waves that are not related to temperature. All bodies at a temperature above absolute zero emit thermal radiation. Radiation is a volumetric phenomenon and all solids, liquids and gases emit, absorb or transmit radiation to varying degrees. However, radiation usually considered to be a surface phenomenon for solids that are opaque to thermal radiation such as metals, woods and rocks, since the radiation emitted by the interior regions of such material can never reach the surface and the radiation incidence on such bodies is usually absorbed within a few microns from the surface. The maximum rate of radiation that can be emitted from the surface at an absolute temperature Ts is given by the Stefan-Boltzmann law as Q emit equal to sigma A into T power 4, where sigma equal to 5.67 into 10 power minus 8 watt per meter square Kelvin power 4, and R power 4 is the Stefan-Boltzmann constant. The idealized surface that emits radiation at this maximum rate is called a black body, and the radiation emitted by a black body is called a black body radiation. The radiation emitted by all real surfaces is less than the radiation emitted by a black body at the same temperature and is expressed as Q emit equal to sigma A into T power 4, where epsilon is the emissivity of the surface. The property emissivity, whose value is in the range of 0 and 1, is a measure of how closely a surface approximates a black body for which emissivity equal to 1. The emissivities of some surfaces are given in the form of another table. Another important radiation property of a surface is its absorptivity alpha, which is the fraction of the radiation energy incident on a surface that is absorbed by the surface. Like emissivity, its value is in the range 0 less than 1. A black body absorbs the entire radiation incident on it. That is, a black body is a perfect absorber, alpha equal to 1, as it is perfect emitter. In general, both the emissivity and absorptivity of a surface depend on the temperature and the wavelength of the radiation. Kirchhoff's law of radiation states that the emissivity and the absorptivity of a surface at a given temperature and wavelength are equal. In many practical applications, the surface temperature and the temperature of the source of incident radiation are of the same order of magnitude, and the average absorptivity of a surface is taken to be equal to its average emissivity. The rate at which the surface absorbs radiation is determined by Q absorbed equal to alpha into Q incident, where Q incident is the rate at which radiation is incident on the surface and alpha is the absorptivity of the surface. For opaque surfaces, the portion of incident radiation not absorbed by the surface is reflected back. The difference between the rates of radiation emitted by the surface and the radiation absorbed is the net radiation heat transfer. If the rate of radiation absorption is greater than the rate of radiation emission, the surface is said to be gaining energy by radiation.